Okay, we're going to talk about Earth's atmosphere and greenhouse gases. So we're looking at a picture of Earth from space, and you can see that beautiful blue glow that is outlining the planet there, and that is our atmosphere. And what you want to notice about it is how thin it is. So, the atmosphere is so important, and we talked about it, for weeks and weeks when we're talking about weather, and we're going to be talking about climate change, and of course, the atmosphere plays a key role in that. So we just want to keep in mind how thin it is in comparison to the size of our planet. In comparison to the 4,000 mile thick radius of Earth, give or take, the atmosphere is about 60 miles thick, so super thin. Okay, so the gases that make up our atmosphere are shown on this pie chart. And while oxygen is something that comes to mind immediately when we think about the atmosphere or the air, because of course that's what keeps us alive, it's not the major component. 78% of our atmosphere is made up of nitrogen, and it comes in the form of N2, and which is two nitrogen atoms stuck together. Oxygen also comes as a diatomic molecule, so the oxygen that's floating around is two oxygens stuck together. And you can see, of course, carbon dioxide is part of our atmosphere, and while we're going to be talking about it a lot in this unit because of the role it plays in warming, it's actually a very small component of the atmosphere. This pie chart showing it at 0.04%. So sort of like, even though our atmosphere is super important, it's a very small part of our whole Earth system, carbon dioxide is a very small portion of the atmosphere. And then there are other gases up there, mostly argon, but methane, nitrous oxide, you could go on and on for the other gases that are in the atmosphere in very small quantities. So now we want to remind ourselves what happens to the energy from the sun as it enters our atmosphere and hits the planet. And this diagram that I have here, you can see we've very much exaggerated the atmosphere so that we can actually draw on it and see what's going on. But do remember that it's super thin. So this is very exaggerated. So let's start with some yellow arrows of energy, shortwave radiation coming from the sun and reaching us down on the planet. So it would help if I spelled it correctly. Shortwave energy. And if you remember when we were talking in the weather unit, we spent some time emphasizing that it isn't the energy directly coming from the sun that heats up the atmosphere. It's actually the fact that that sun energy hits the planet, warms the planet, and then the planet re-radiates heat back up. And you can see now I've changed the pen color and I'm making my waves larger to represent the fact that this is now infrared energy, which is a longer wavelength. Infrared is essentially heat. So infrared radiation it gets re-radiated up from the surface, and this is what warms the atmosphere. And you can see I've drawn this arrow escaping our atmosphere and going back out into space, which of course happens. But what we want to talk about here is the fact that not all of it escapes. And if we go and add some little molecules into the atmosphere, so I'm just going to add some dots here to represent some of those molecules of oxygen and carbon dioxide and nitrogen and the other gases we were talking about. What happens is that some of the infrared radiation that's coming up from the planet interacts with those molecules. And if that radiation hits a greenhouse gas molecule, instead of just continuing out up into space, it gets absorbed by the molecule and then re-radiated in a different direction. So it could be back down towards the surface. It could be back up out. it's sort of random which direction it gets re-radiated. So what was headed out to space may now be bounced back down towards the surface. So essentially, that radiation got trapped in the atmosphere by interaction with the greenhouse gas. Right, so this is a PhET interactive that helps us look a little bit at what happens when energy from the sun interacts with the molecules in the atmosphere. And you can see, so we've got this flashlight, and I have it set to visible photons, which is going to represent sunlight. And this green that I drew down here is just to remind us that we're sort of pretending we're looking down at the Earth. So what I'm going to do is I'm going to populate this space with some molecules representing our so we're adding some nitrogen N2 molecules, and we're going to put in a bunch because that's the biggest portion of the atmosphere. We'll add some oxygens, maybe we'll add a little bit of CO2 and some methane for good measure. And we're just going to hit go. And these photons are representing sunlight traveling from the sun through the atmosphere down to Earth. And you can see there's no interaction, right? Those photons are passing through all of those gas molecules and not being impacted in any way. So now what we want to do is we're going to switch and think about what happens once the energy from the sun has hit the planet and has been converted into the long wave infrared heat that is re-radiated back. So we have to switch our frame of reference now, because now the flashlight is Earth. This is the surface of Earth radiating heat through our atmosphere, and now the sun would be on this side, but we can't see it. So I'm going to turn our interaction back on here. So this is the Earth re-radiating the infrared radiation, and you can see right away that especially this carbon dioxide molecule is interacting a lot with these infrared photons. And here's some more carbon dioxide. You can see the methane is interacting, and when a photon interacts with the greenhouse gas, you can see that it gets bounced in a different direction. Sometimes it does continue out towards space, but sometimes it gets bounced back down. And we can really emphasize that. Let's really jack up the carbon dioxide molecules here so that there are more to hit. And well, let's just go all the way here to 15. And if you watch it for a while, you should start to notice that the number of photons that actually make it out this side to space, let's see, can we see that it's less than all of the other sides? It's a little hard to quantify, but definitely photons are getting bounced around back in directions other than the direction they started in. All right, so greenhouse gases. I've got a list of a few of the major ones here, as well as some of the natural sources of how they get into the atmosphere, and then we're going to add in some of the human sources. So starting with carbon dioxide, CO2. You learned about the carbon cycle before, so decaying and living organisms, volcanic eruptions, all those things put carbon dioxide into our atmosphere naturally. But what humans do that puts it up there is we burn fossil fuels. So driving cars, all our factories, anything that takes energy, burns gas, oil, natural gas, it all puts carbon dioxide into the atmosphere. Okay, water is also a greenhouse gas. Okay, this is really not working all of a sudden. And again, that is definitely, that's natural. All the water cycle processes we've talked about so much, evaporation. And basically, humans aren't a significant additional source of water into the atmosphere, but I put it on the list just to make sure that you know that it is a greenhouse gas. It is up there bouncing those infrared energies back towards Earth. Okay, methane is a good one, CH4. Okay, decaying organic matter puts it up into the atmosphere naturally. What we do is coal and natural gas production. Okay. And then the other thing is agricultural related. So it turns out actually that livestock farts actually emit a lot of methane. And of course, we grow livestock for food production. So there is a lot of livestock on the planet that wouldn't be here without us, and they are all farting methane. Last one, nitrous oxide, N2O. Bacteria in soil and ocean produces nitrous oxide. We also, with agricultural and industrial processes, and also wastewater treatment processes. So I'm not even going to try to write anymore. I'm sorry this got so messy at the end. At least we got our diagrams done. Okay, good job, guys. Thank you.